So we'll go to, actually I'm going to try to get to the end of chapter 12 because they summarize all the rules there. Okay, so here's the rules. And we've already said we can't use the power rule, so it's got to be something else. Which one of those functions that you see there has a derivative of 1 over x? The natural log function. This one right here. Okay? So that's going to help us actually do this problem that we're working on, because we've determined that this is actually 1 over u, and here's the du. And since this is 1 over the function and we have that function's derivative, then this is going to be then the natural log of that function. And technically you should, this is technically you should say that it's the absolute value of this function, because we know that this quantity can't be allowed to be negative. But that I'm aware of, there wouldn't be a number large enough or negative enough to put in for x in this case, that 3 times that negative number would be more than that negative number squared, which is going to be a very large positive number. So in this case, the absolute value bars are kind of redundant. You don't actually need them, but I'm just reminding you that you can't take natural logs of anything that's negative. And then, of course, the last part of that is we have to have our constant of integration. So this is actually the integral of the function that they ask us to find. Does anybody have any questions, or is it coming back now? You haven't done this for about a week, so you might be a little rusty. Okay, let's try another one. And this is example 5. And we have an integral that is the integral of x squared times e to the x to the third dx. And the e to the x to the third looks like a more complicated thing to deal with to me than the x squared does. So in this case, if we choose u to be e to the x squared, then what we really have for u is e raised to some power that is a function. So actually what this is, since this is the function, it's actually being used as a power on e, it's going to be the integral of e to the u and then the derivative of u. So the reason we need to specify that is because we need the derivative of x to the third. And the derivative of x to the third is what? 3x squared. And of course, we're going to always just bring along that dx. And we have x squared dx, but we don't have a 3. And we need to put in that 3. So if we put the 3 here so that we have du, where else do we need to put a number in that we can take the 3 back out? What else do we need to do? We have to multiply twice. Okay? We've multiplied once by 3. What's the other number we need to multiply by that will take the 3 back out? 1/3. Very good. So now what we have is 1/3 times the integral of e to the u, and we have du, that's the derivative 3x squared plus dx. And the integral of e to the u, basically we're saying what function has e to the u as its derivative. So if we go back and look at the rules again, we know that the derivative of e to the x is e to the x, right? So it stands to reason the derivative of e to the u is e to the u, and therefore it is also not only its own derivative, but its own integral. So that's going to be 1/3 times e to the u, but then e to the u is actually x to the 3rd. Not e. E raised to the power x to the 3rd, and then of course plus your constant of integration. Any questions on that one? So with that one done, we have some rules for calculating integrals. And you'll be allowed to have these rules on the test. You'll also have the rules for derivatives in case you forget one. So this is the summary of your rules. We have a power rule that we can use with substitution, where the power is n and the function is raised to the nth power as long as n is not equal to -1. That's going to present a problem. And the way that we do that is we take whatever that function is to that power, we add 1 to its power, and then divide by that new power, n plus 1, and add a constant. But then once we get that u raised to the power, we put that function back in. The second one is saying the integral of the derivative over the function itself. So this is the same as writing 1 over f of x and just dx, because it's derivative of whatever f of x is. And the way that we do that is if you've got 1 over a function, its derivative is the natural log of that function. So you simply put the natural log back over on the other side and you plug the function back in, add your constant. If you have e raised to a power, the power becomes the u, and its derivative has to be present. But once you've got that, then the result is e raised to that power plus a constant. And if you had to add in another constant outside the integral, then you bring that in. Now since I know you've slept since then, I'm going to work this one with you, but I want you to give it a shot. So I'm going to give you a few minutes, and you can talk among yourselves. But I want you to see if you can do this one. You've got all your rules. They're on your handout. See if you can do that problem. The integral of x times the square root of 1 minus x. And I will get you started. So there's your function. Take about 2 or 3 minutes and see if you can do the problem. I'm going to get a drink of water, let you talk to your partners about it. You can share as a class. Let's see if you can do that one, and when I come back in, you tell me what you think the answer is. Come to consensus. Anybody have any brilliant ideas? No? How much have you spent in a homework? How much money? One more time. I understand. Scott, what do you think U is? And that's because 1 minus X is in the middle of a chain rule type problem, right? Okay, if U is 1 minus X, Matt, what's the derivative of 1 minus X? It's negative 1. But then we've got that X sitting up there. What the heck are we supposed to do with that? Because it didn't say anything about X having to be part of the derivative. Any ideas? Well, okay, here's the problem, and yes, I left you with one that was challenging. Here's the problem. If we choose this to be u, then the derivative of that, which is du, is 1 minus 1, or 0 minus 1. So du is only negative 1 dx. Now, if all we needed was a negative 1, no problem. We could put a negative 1 out here and a negative 1 inside. Got it fixed. We still have a piece of the puzzle hanging out here that we haven't done anything with. And it just can't sit there and be in the way. It actually has to be part of everything. We don't have any leftovers in calculus. So what we're going to have to do, rather than try to approach it with that being u, even though that seems like a really good idea, the only issue with it is that we have the wrong derivative for that to happen. So maybe we rethink what u is. Now there's one other possibility. We could choose, since x, f of x equals x, that's function. Y equals x is a function. So maybe we let x be u. Let's try a different approach. So we'll let that be u. If that's u, then this is also u. And we can actually multiply those together if this is going to work. So the question is, if this is going to work, what is the derivative of x? 1, positive 1 dx. Well, we've got positive 1 dx. So there's du. Now we need a way to deal with this. And the way that we're going to deal with this is we're going to take the integral of, let's see. I think I may have seen an easier way to do this. Because multiplying this out is not going to be easy either, because we have that power sitting there. So we need to maybe think another strategy. Now, let's just start off on another piece of paper. So we're trying to take the integral of x times the square root of 1 minus x dx. And we're trying to figure out a way to have u. Let's go back to Scott's idea that this is u. Then du is minus 1 dx. And clearly we can put a minus in here and a minus out here and we can have that. That's not a problem. But then the question is, if this is u, what the heck is that? So we're saying, okay, we've converted this to where this is the integral of the square root of u, and we have du with the dx. If 1 minus x is u, then what's x in terms of u? Say it again.
1 minus.
Yes. Yes, x could be 1 minus u. Or maybe, actually better if we turned it around, we said it was u minus 1, because u is 1 minus x, and this has the opposite sign.
Yeah.
So maybe we need to call it x minus 1. Which meant, well, not x minus 1, it's actually u minus 1. X is equal to u minus 1. Now this is the part where it's going to get tricky for you to understand, so I'm going to try to explain over here. We have u is equal to 1 minus x. We need to have this in terms of u, so we need to know if u is 1 minus x, what's x by itself? So if you do that, then you subtract 1 from both sides, and you have u minus 1 is equal to negative x, but that sign is turned around the wrong way. That's negative x. So we have to turn it back around into 1 minus u, but it turns back into u minus 1 because we have this negative out front we can get rid of now, because negative 1 times 1 minus u gives us back u minus 1. So our integral actually looks like this. The integral of u minus 1 square root of u du. And in this case, u is equal to 1 minus x, so that's where we got the square root of u from. And then x is equal to 1 minus u, but because we have that negative that we had to bring in from here, it's going to flip this back around to be u minus 1. And then we don't have to have the negative on the outside. Now I know it doesn't look an awful lot better, but we can actually do this one now. Because this is the integral of u minus 1 times u to the 1/2 power. And we can multiply these together where we couldn't do it before, because we'd have had to have applied the power before. We'd have had to have applied the power to both things in the parentheses. This time we only have to apply the power rule because we have 1 u. So u times u to the 1/2 times u minus 1 times u to the 1/2. Of course, we still have du sitting out here. Becomes the integral 1/2 times u to the 1/2 times 1 is u to the 3/2. And negative 1 times u to the 1/2 is negative u to the 1/2, and then we still have du. So this is the u substitution that we made. We had to be creative about how we made it. This is just a power rule now. We can break it up into 2 pieces and do each term individually. Both of these have their little du after them. But the integral of u to the 3/2 is u to the 3/2 and we add 1 to the power. And then we divide by that new power. And then we subtract, and we take u to the 1/2 and add 1 to the power and divide by that new power. And of course at the end we're going to add a constant of integration when we get finally finished. So 3/2 plus 1 is, 3/2 plus 2/2 is 5/2. And 1/2 plus 1, 1/2 plus 2/2 is 3/2. And since we're dividing, rather than divide by 5/2, we're going to multiply by 2/5. And instead of dividing by 3/2, we're going to multiply by 2/3. And then at the end, we're just simply going to put back in our u substitution. So our u, from way back up here, u is 1 minus x. And of course, then we have a constant. So there's what your final answer actually looks like. Now you could convert it back into radicals, but there's no need to. Okay? Now, I'm going to tell you up front, if you can do that one, you have no problems with the test, because that one is challenging. That one's very challenging. So if you need to, you may want to go back and watch how that one works again. Or if you want to go over it, the explanation for it is also in your e-text for example 5. But when I looked at it, I thought, yeah, they're leaving out a lot of details. We need to talk about that one. So our last problem in this section is a problem. It's an application problem, and it's about demand. Research department for a hardware store, a hardware chain, has determined that that at one store the marginal price, remember marginal price is a rate of change of price, which is to say it's a derivative of X boxes per week for a particular type of nails, is given by this, and P prime of X, of course, is marginal profit or marginal price. And this is the expression they gave us, and it says to find the demand equation if the weekly demand for this type of nails is 10 boxes when the price of a box is $4. So what we're actually trying to do an integral of is negative 4,000 over 2x plus 15 raised to the third power dx. And from there, it seems hopefully pretty obvious that that would be u. And we need the derivative of u, which would be 2 plus 0, which is 2, dx. Now what we in fact have, and I'm going to separate this out a little bit, going to turn that into a power expression. What we actually have is negative 4,000 dx, so we only need 2 dx. We've got way too much. So what we need is we need a multiplier that will take out that 4,000 and leave the 2. So the way that we're going to handle that, we're going to swap out negative 4,000 for the 2, and on the outside we're going to pull the negative 4,000. And since we multiplied this by 2, we're going to divide this side by 2. So that means our actual integral looks like this. Negative 2,000 times this to the negative 3 power du. So when I integrate u to the negative 3 power, what I actually get then, let's see, negative 3 plus 1 is u to the negative 2 power. And I'm going to divide that by negative 2. But then I've still got this negative 2,000 out here. And of course I'm going to add my constant. Negative 2 goes into negative 2,000 1,000 times. So what we have now is 1,000 u to the negative 2 plus a constant, which is exactly the same as 1,000 over u squared plus the constant. And at this point, since this is the simplest form that we can get, we'll go back in and substitute 2x plus 15 for u. And that's plus our constant. So there is the final form of our integral, and this is actually the demand equation, except we don't know what the constant is. But what we do know, if we go back to the problem, is it says that 10 boxes is the demand when the price is $4. And since the demand is the demand price, that means we've got $4 is equal to 1,000 over 2 times 10 plus 15, quantity squared, plus the constant. And the only thing we don't know then is the constant. So we'll do a little bit of arithmetic. 4 equals 1,000 over 2 times 10 is 20 plus 15 is 35 plus the constant. And 35 squared divided into 1,000 actually turns out to be about 0.82. Since it's money, we can round to 2/10, and I think it might actually come out even. Let me grab a calculator and see. No, it didn't quite come out even. I wasn't sure if I remembered it did or it didn't. But 0.82 is close enough because, like, you know, this is in dollars. So that's 82 cents. Plus a constant. So that means the value of the constant for the demand formula is $4 minus that 82 cents. So that's 3.2 or 320. Wait, 82 cents, sorry. So it's not 320. It's $3.18. Sorry about that. So this means our demand equation, the price at which X units are demanded, is given by 1,000 divided by the quantity 2 times the number demanded plus 15, quantity squared, plus $3.18. There's your demand equation. So that's the demand for X boxes at P dollars. Now that actually finishes the first section. We've got about 15 minutes left. I want to talk to you a little bit about what the idea of a definite integral is. These, up to this point, have all been indefinite integrals. We need to talk about what a definite integral is. We're not going to get finished with it, but I want to at least give you the idea. So hopefully you've already got the notes for the whole chapter. And this is more visual. There's not going to be a lot of math work to do for this. And there's some arithmetic, but it's not arithmetic we can't handle. So we want to talk about area in the definite integral. Here's a problem that we're actually going to solve in this particular section. If we know the rate that oil is leaking from a machine varies with time, and sometimes it's more, sometimes it's less, how can we estimate the total amount of leakage over a certain period of time? Now, if you think about the machine being an ocean-going boat, you can see why knowing how much leakage there's going to be over a certain amount of time might be important, because you don't want an oil slick. So we're going to do this in example 3, but first we need to develop the idea of how can we go about doing this. Now, if you were pretty good in geometry and you like geometry formulas, this might make an easier understanding for you, but if you can visualize using pictures, the geometry part is not hard geometry like making proofs and stuff. It's a matter of visualizing how do you find areas of things. So if we had, and this is not a useful one, but this is one just to give you the idea. If we had the region bounded by the y-axis, which is f of x, and the x-axis, and we have the graph, which is the square root of 4 minus x squared. The square root of 4 minus x squared gives us a quarter of the equation of a circle. The reason it only gives us a quarter of the equation is because we've been restricting it here to the first quadrant. What if I wanted to find the area in that blue region? How hard would that be? How do you find the area of a circle? Anybody remember that formula? Formula for the area of a circle is pi r squared. What does r stand for? Radius. What's the radius of this circle? 2. Okay. So if the radius is 2, then the area is the number pi times 2 squared. So the area is equal to exactly 4 pi, but since we'd like to have a decimal approximation we can use to compare later, there's pi times 2 squared is 12.56637. And that's enough decimals for us to be able to make a comparison. Okay, so that's the actual area. That is the exact actual area. Now we can approximate that area by trying to use rectangles instead of circles, because the formula for finding area of rectangles is far simpler than the formula for finding the area of circles. And actually I forgot to do something here, that since it's a quarter of a circle, let me pop back over here to this again, it's actually, since it's a quarter of a circle, needs to be divided by 4. So actually, if I divided that by 4, the area is actually just pi, which is 3.1415, blah, 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 blah. Okay? So if I was trying to approximate it, and I don't have a good rationale for why we would want to approximate it, other than later on, nothing is going to be as easy as using a circle for the formula. What I could do is I can divide this radius at the 1 mark, and I can make a rectangle that's 2 units tall, and then make another rectangle and if I were to calculate the area of these, then both of these are 1 inch, 1 unit, let's say, not necessarily inches, but 1 unit wide. This one's 2 units tall, but the question is, what would be the height of the second rectangle? So if we look back at the second rectangle, what you need to do is substitute in 1 into the equation. And you get the square root of 3. So the height of that one is the square root of 3. So that means that this is 1 times the square root of 3, or the square root of 3 units, and this is 1 times 2, or 2 units. And if I add these two rectangles together, the total area, I'm pointing at the wrong thing. Y'all are totally confused. Sorry. So if I know this is the square root of 3 by plugging back into 4 minus 1 squared, I get the square root of 3, which is the height of that second rectangle. And the square root of 3 times 1 gives me an area of the square root of 3. And then the height of this rectangle times 1 unit, height times width is 2. So the approximate area would be 2 plus the square root of 3, which would be 3.73. And notice when you compare that 3.73 to the 3.1415, we've overestimated. And we know we overestimated because we can see that this rectangle goes outside the circle by that much. And this rectangle goes outside the circle by that much. So it's an overestimation. Now the other method we could use is we could instead use what are called inside rectangles. And if you use inside rectangles, this is the square root of 3 tall. And unfortunately, we have no way to estimate that with a rectangle because we can't draw a rectangle inside this that even comes close to approximating that. And if we take that to be just the square root of 3, because this is all the area that we're estimating with, we don't have an interior rectangle we can draw there, then it vastly underestimates the area because it leaves out all of that and all of that. So neither one of those estimates is very good. But you could improve the estimate a number of different ways. One of the ways you could improve it would be rather than trying to draw outside or inside rectangles, you could try to select a midpoint. And choose the rectangle to be at the midpoint. So if these were your two rectangles, notice what happens here. You got a little bit of underestimation coupled with a little bit of overestimation. And here you got a little bit of underestimation coupled with a little bit more underestimation. These rectangles are both 1 unit wide, but their heights are different. F of 1/2 is 4 minus 1/2 squared, and then take the square root. and it's 1.93 for the first rectangle. And then this would be f of 1.5. And then take the square root of that. And that will be 1.32. We'll call that 1.323. So if I add 1.93, actually we'll call that 1.94. We're going to round it to 2 decimal places. If I take 1.94 and 1.33, I get 3.27. And 3.27 is a lot closer to the actual area. Okay? So there's 3 different ways you can use just 2 rectangles to estimate the area, but the one that gives you the better estimate is the one that you center over the midpoints and divided it up evenly and centered it over that 1/2 rather than making it completely as tall as the circle or even only as tall as the other edge. Those are called left rectangles, right rectangles, and midpoint rectangles. Only the midpoint even comes close to being the right answer. Now from there, I'm going to skip back over to the PowerPoint because we're almost finished here. And that just summarizes what I just finished telling you. One thing you could do is you could use 4 rectangles instead of 2. And notice here that if I use 4 rectangles instead of 2, if I have them be left rectangles, then there's a little bit overestimation, a little more overestimation, a little more and a little more, but I get back down closer, okay, with more rectangles. There's not as much area that's left out. If I used 8 rectangles, I'm dropping the whole area down to 3.3398, which is again closer to 3.1415, because the part that's hanging outside the circle is getting smaller. Now imagine, if you would, making 16 rectangles, which is going to take a lot of arithmetic. You would get closer. If you made 32 rectangles, you would get closer still. I'm going to skip back to that for a second and look at this. Which one of these 2 drawings is going to give the best approximation to the area under the curve between A and B? The one on the left or the one on the right? The one on the right. Why? More rectangles means there is less error. Because if you look at these little bits of white up here along the tops of those bars, those little bits of white are the amount that it's underestimating. Over here, the amount that it's underestimating is considerably more because you have fewer rectangles. Now, if I could cut these 20 rectangles into 40 rectangles, it would be very close indeed. Or if I cut that into 80 rectangles, I would get closer still. There would be very little error by the time I get to 80 or 100 rectangles. And this one says, you know, you could probably do 500 rectangles and get really, really accurate. So rather than dwell upon that, in order to get a process that's going to yield the exact area, what we're going to do is we're going to take B minus A, which is the distance on the 2 limits, the sides of the area, and we're going to divide it by some number n, and each one of those B minus A over n's is going to be one little incremental change in x. Now, if you only change x by 1, the estimation is not very good, because that's 1 rectangle, 1 unit wide. If you make your rectangle a half a unit wide, the estimation gets better. If it's a fourth of a unit, it gets better still. If it's a hundredth of a unit, it gets really good. If it's a thousandth of the interval, then it gets practically indistinguishable from the real thing. Now, I hate to bring up a subject I know that none of you are fond of, but does this sound anything like a limit to you? I'm letting the change in x get smaller and smaller and smaller and smaller, and as I let that change in x get smaller, that means I have more and more and more and more rectangles, which means the improvement of my estimate gets better and better and better and better and better. And that basically is how we're going to find area under a curve, is we're going to let the width of those little rectangles approach 0. It can't be 0 because then you don't have a rectangle, you have a line. But if I let it get as small as I possibly can, let it approach 0, I'm going to get a good approximation. And you don't have to worry about making the tables and stuff because we're not going to do a lot of that. I'm just going to tell you what the definite integral is. The definite integral is calculated by finding the sum of the areas of n rectangles as n approaches infinity. More and more rectangles means the increment of x gets smaller and smaller and smaller. And on the interval from a to b, where those are the values that are in the domain of the function. We're going to end up here. And then we'll come back and learn how to do this without going through a lot of geometry. Unlike the indefinite integral, which even if you could find the value for the constant, you're getting a formula. What we're finding now is the definite integral represents a number, and that number is area between some function and the x-axis. Okay? It's the area under a curve. It has a meaning. So where we're going to pick up next time is the part that you're going to want to learn how to do, which is how do I do this with my calculator and get the answer? Okay? How do I put those numbers in my calculator and get the answer? So that's where we're going to start. Be sure you have your calculator with you next time, and I will see you on Thursday.